Welcome back everyone. In this lecture we will actually study this fixed subspace. As I promised, we will actually prove there is this projection map from V to the fixed subspace. We will understand how the projections work. So let me just first recall what is projection and then the properties of the projection. So this is actually somewhat basic linear algebra. If we have a subspace W of V, then the projection is an onto map from V to W is a projection on W if the following property satisfies. When you restrict P to W, then we get identity on W, and the second property is P square is equal to P. So, sometimes actually people define projection is a map from V to V. So, basically W is the image. So, I am just putting the conditions in the definition. So, now once we have the projection, it is immediate that you can actually always decompose V into direct sum of its kernel and the image. So, you have this kernel and then you have the image. So, it is easy to see that the image of P is W because P restricted to W is identity. So, let us prove this. It is immediate that if you have element in the intersection, so then that is supposed to be 0. So, let V from this. So, then it is immediate that PV is 0 and PV equal to V as P restricted to W is identity W. So, that will imply that V is 0. So, that proves that kernel P intersection W is always 0. So, now let us prove why the sum is equal to full space. So, let V being an element in V. So, then you can write V as PV plus V minus PV. So, now if we take this V minus PV and then apply the operator P, it is immediate that this is exactly PV minus P square V, but since P square is nothing but P, so that is part of the definition. So, that immediately implies that this is exactly PV minus PV, which is equal to 0. So, that implies that V minus PV is indeed in the kernel P, and obviously PV is in the image P, which is exactly W. So, that proves that V is nothing but sum of the kernel and then the image. So, now how the matrix of P looks like with respect to this decomposition. So, V is nothing but kernel P direct sum of this image P, which is exactly W. Now, we can fix the basis B1 of this. So, this is the basis, and then again fix another basis B2 of this image P. So, then if you look at the map P with respect to the basis B, which is obtained by putting together the bases B1 and B2, then it is immediate that on the kernel it is going to act as 0. So, you get only the 0 matrix, and here again 0 0 because both are P invariant subspaces. Now, on image P, which is exactly W, so that on which it is just identity map. So, when you restrict to the W, then you get identity here on W. So, this is how the matrix of the projection looks like. Now, if you look at it from this, we will be able to say everything about the projection. For example, the rank of the projection, which is nothing but the dimension of the image space, is going to be exactly the dimension of W, and the nullity of the projection is going to be the dimension of the kernel of P, which is going to be exactly the dimension V minus dimension W. So, these things are immediate for the projections. So, now let us go back to our representations. So, like said, we started with the representation phi from G to GLV. So, then we define this fixed subspace, which is those vectors in V which are fixed by all the elements of G in G. So, what we want to actually understand what will be the dimension of this Vg. So, we want to understand the dimension of Vg, and for which we are going to use the projection that we defined before. So, recall the projection phi p phi which is defined from V to Vg given by taking element V and then taking the average sum of that over G in G, and we verified that this indeed belongs to Vg. So, that means this P phi defines actually a map from home V Vg for complex number. Okay. Now, if you think about it, it is not just a homomorphism linear map. This also actually satisfies the following conditions. The very first condition is this phi restricted to this Vg is going to be just identity on Vg. So, that is because let us take V in Vg. So, then that immediately implies that each element in capital G fixes this V for all G and G. So, then that means if you look at the image of this P on this V, it is going to be average sum summation G dot V, V in V. So, since this each individual G dot V is V, so then all we get is the cardinality of G times V divided by the cardinality of G, which is exactly V. So, this proves that the map that we define restricted to Vg is nothing but the identity map. Indeed, one can check this is indeed projection, that means the square of P is going to be itself. So, let us verify this. So, let us take some vector V in capital V, then let us apply this P phi on this vector. So, which is going to be the cardinality of G 1 divided by the cardinality of V G, G in G, G dot V. Now, note that this element is going to be some u which is there in Vg. So, that means if we apply P phi on this P phi V, so then you can easily see that this is going to be again P phi applied on u, but we already know that P phi restricted to this Vg is going to be identity. So, this is going to be exactly u. So, this implies that P phi square applied on V is exactly u, which is nothing but P phi V. So, that means this P phi square is exactly P phi. So, that means this is indeed a projection. So, now using the general destruction that we had before, that immediately tells you that this V can be decomposed into kernel of this map P phi and then the image which is exactly Vg. So, in particularly the rank of this projection P phi is nothing but the dimension of Vg. So, now if you think about it, so the rank also like can be reinterpreted in terms of the trace of the matrix. So, we can actually choose the basis B1 of the kernel and then the basis B2 of the image. So, then we realize that the matrix of this projection with respect to the basis, which is the union of B1 and B2, is going to be exactly the block matrix which has 0 0 on these 3 places and identity on this image, which is identity on Vg here in this right bottom. So, in particularly the trace of this P phi is going to be exactly the trace of this matrix, which is exactly the dimension of V G. So, this is indeed striking observation. That is because the trace of this map P phi can be actually computed using the average map. So, note that P phi is nothing but the average of all the actions of this G in G. So, in particularly the trace of phi phi is going to be 1 divided by the cardinality of G summation the trace of phi G G in G. So, putting them together you can see that the dimension of this fixed space is nothing but can be computed using this quantity, which is the you take the sum of all the possible traces of phi G and then take 1 divided by the cardinality of G. So, that is going to be the fixed space dimension. So, for some reason if we know that this quantity is non-zero, then that will make sure that the dimension of V G is actually non-zero. So, this is actually kind of gives us some information about the dimensions in terms of the trace of the each operators. So, this is actually somewhat important result to remember. So, this we will be using a lot in order to prove orthogonality of irreducible characters. So, maybe when it is needed I will again recall this result. So, you can already see that trace started appearing already in order to compute a dimension of this fixed subspace. So, that means the traces are actually going to play some important role in representation theory. So, that is indeed the case. So, let me actually motivate why these traces actually kind of play an important role. So, basically character theory is all about understanding the traces of all these operators. So, to understand that let me first recall the important fact about the diagnosability of all these operators. So, here is the motivation for the characters. Okay, let us fix a representation, finite dimensional representation. So, everything is finite dimensional and the group is also let us say finite. So, now given this representation we want to understand how this representation act on this capital V. Okay. So, each element of the group how it acts on the capital V, that is what we are interested in. Since the group is finite. So, given any G in G and we know that G power order of G is going to be identity. So, that would imply immediately that rho of G power order of G is going to be identity matrix. So, that means the minimal polynomial of rho of G is going to divide this x power order of G minus 1. So, that means rho of G is a diagnosable operator because the minimal polynomial has distinct roots, and not only that the roots of or the eigenvalues of this rho of G, they are all O of G the roots of unity. So, maybe let us call this maybe capital N to be the order of the group. So, if we use the order of the group, we can replace this O of G by this common number capital N. So, it is immediate that the minimal polynomial of this rho of G divides this x power n minus 1. So, in particularly the eigenvalues of this rho of G, they all live inside this nth roots of unity. But what is important for us is that rho of G is diagonalizable. So, since it is diagonalizable, there exists a basis B, let us label it as V 1 etcetera V n, such that this rho of G act on this basis as these eigenvalues lambda I V n. So, let us say lambda 1 etcetera lambda n, it is the eigenvalues of this rho of G, of course counted with multiplicity. So, now we have very explicit action of this rho of G on this basis V I, which is given by lambda I. So, that means if we understand these eigenvalues, of course up to reordering and so anyway we only talk about its action on the basis, we do not need to worry about the order and all. If we understand this multiset, that is the set of eigenvalues lambda 1 etcetera lambda n counted with multiplicity, then that means we understand the action of rho of G on this given vector space V. So, that actually kind of motivates us to actually look at these eigenvalues, and of course, the eigenvalues, the information is completely stored in the characteristic polynomial. So, let us call this chi of A x to be the characteristic polynomial, which is the determinant of rho of G. Okay, I am using A. So, this is A minus x times identity. So, this is the characteristic polynomial. So, in order to understand the diagnosable operator, it is enough to understand the eigenvalues of that operator counted with multiplicity. That means, it is enough to understand what is the characteristic polynomial of that operator. So, we are of course hiding lots of information under the carpet, how to factorize that characteristic polynomial and so on. But using the fundamental theorem of algebra, so we know that any n degree polynomial has n roots. So, storing the data of the roots is same as storing the data of this polynomial. But if we think about it, the polynomial actually the coefficients of the polynomial has a very deep relationship with its roots. So, let me just rewrite and then we will see. So, we can take A to be diagonalizable operator, okay, because anyway we are going to look at only rho G, which are all diagonalizable operator. So, with the eigenvalues, let us say lambda 1 etcetera lambda n. So, this is the dimension of the matrix is n. So, this is the eigenvalues, of course like I said counted with multiplicity. So, now the observation is that A is determined by its eigenvalues and the eigenvalues determined by the characteristic polynomial. Now, if we actually write down the characteristic polynomial in terms of the eigenvalues, then you get exactly the product of x minus lambda I range from 1 to n. So, if you expand this thing, then what you get, you get exactly the characteristic polynomial, that means the coefficient of the characteristic polynomial in terms of the roots lambda I. So, that means you can expand this and then see that you get exactly x power n e 1 x power n minus 1 plus e 2 x power n minus 2 and so on. Then finally, you get minus 1 power n e n. So, where what are these coefficients e 1 etcetera e n? They are nothing but the elementary symmetric polynomials. So, they are very explicitly given in terms of the roots. So, here we can easily see that. So, I will leave it to you to actually do this exercise. These E k's are actually given by this elementary symmetric polynomials of on this roots lambda 1 etcetera lambda k lambda n. So, this E k is given by very explicitly sum of this lambda I 1 etcetera lambda I k, where the I 1 actually they vary over from 1 to n, satisfying this property. So, with the convention we just write E naught to be 1. Okay. So, now the elementary symmetric polynomials in this lambda 1 etcetera lambda n actually captures the coefficients of these characteristic polynomials. So, in particularly if you are interested in understanding the diagnosable matrix, so one needs to understand this elementary symmetric polynomials that are actually given in terms of this roots lambda 1 etcetera lambda k. But then where this trace indeed appear here, if you think about it, since A is actually diagnosable, so the trace of A is going to be exactly lambda 1 plus etcetera plus lambda n. And similarly, if you take any power of A, so since A is diagnosable, the powers of A are they are also diagnosable. So, in particularly for example, A square is diagnosable, A cube diagnosable and so on, and the eigen values of this A square is going to be just powers that lambda 1 square etcetera lambda n square. So, in particularly the trace of this A square is going to be the squares of this lambda I, sum of the squares of this lambda I. Similarly, one can prove that the trace of A power k is going to be lambda 1 power k plus etcetera plus lambda n power k. So, whatever they are going to be some quantities, and if you close these traces closely, you can see that this is nothing but power sum. This is power sum polynomials. So, usually they are denoted by p k. So, the p k of lambda 1 etcetera lambda n is defined to be lambda 1 power k plus etcetera lambda n power k. But what is the connection between these elementary symmetric polynomials and these power sum polynomials? So, that connection is explained in Newton identities. So, if you know for example, elementary symmetric polynomials, then from them you will be able to compute these power sum polynomials. So, this is called elementary symmetric polynomials in lambda 1 etcetera lambda. So, the Newton identity says, so let me just state it, Newton identity is, this actually gives close relationship between the power sums and elementary symmetric polynomials. So, k times E k is given by summation I ranging from 1 to k minus 1 power I minus 1 E k minus I p I. So, now using this one can actually compute the elementary symmetric polynomials recursively from these power sum polynomials. For example, E 1 is going to be exactly P 1 and then E2 is going to be P1 square minus P2 divided by 2, and similarly E3 is going to be P1 cube minus 3 P1 P2 plus 2 P3 divided by 6, etc. So, if we know PIs, then using PIs we will be able to compute EIs. If we know PIs, so then we will be able to compute EJs. But once we compute EJs, that means we will be able to compute the characteristic polynomial. So, that means we will be able to compute all the roots of the characteristic polynomial. So, we will be able to compute the action of the diagnosable matrix. So, it may actually sound like a little detour, and we are just going around and then trying to understand something. But indeed this is actually very helpful observation that is used in the character theory. So, because once we have an element G in G, then it is immediate that all powers of that element is going to be in G for all k greater than or equal to 1. So, in particularly if we can record the trace of all these rho G powers, rho of G power k's. So, if we record this data, so then from this it is expected that we will be able to say it is expected that we will be able to recover rho of G, as rho of G being actually diagnosable operator. So, that is what actually indeed happens. So, that is what actually motivates us to define the characters, and of course, so this is the crux in the part of the character theory. But so we can't actually just use just one element of G and then its powers to just to recover rho of G, because G has lots of symmetry in it. So, we can use the entire symmetry of the group, and then we will be able to actually record everything about the trace of each element, and then from that we call that as character. From that character, so we may be able to actually recover the entire action of the group on this any given representation. So, that is the motivation. So, that actually motivates us to define this character. So, let me just define the character given this representation from G to GLV, the character of the representation, which is denoted by chi rho, it is a map from G to C. So, given this, define chi rho called the character of rho by chi rho of G is given by the trace of rho G for all G in G. So, this is how we define the character. And like I said, so given element G, so we will be looking at various powers of G, and then using the various powers we will be able to actually take the traces of them, and then from that we can recover the characteristic polynomial of that rho of G. From that we will be able to recover rho of G. So, this is actually kind of what is going on behind the screen, but we will not use something like this to say that character actually determines the representation. So, we will develop some more complicated mathematics using linear algebra, and then we will actually prove that the irreducible characters will form a actually orthonormal basis for the space of class functions. Using such result, we will actually prove that the character of any representation indeed determines the representation uniquely up to isomorphism. So, that is indeed an ultimate goal of character theory. So, we want to say that the characters determine the representations. So, we want to ultimately prove this. But anyway, so before actually getting into the hardcore part of the character theory, so let me actually quickly give the proof of Newton identities. I believe like most of you must have seen the proof, but anyway, just to be complete, let me just quickly actually give the proof of Newton's identity. So, here is the proof. Proof is actually somewhat very simple. So, let me actually just work with some very general polynomial with some roots xi. I range from let us say 1 to n, and this you can rewrite it as from I range from 0 to n minus 1 power k minus I e k minus I x 1 etc. x n t power I. So, there are let us say n roots x 1 etc. x n, and then we have this identity, and this is there. So, one can treat this as a formal identity where x I is also you can take it to be formal variables and t is also formal variables. So, now all we do is just a formal computation. So, if you substitute t equal to x j, so then we get on the left hand side is 0, but on the right hand side we get summation I range from 0 to n minus 1 power k minus I e k minus I x 1 etc. x n x j power I. So, this we get it for each j from 1 to n. So, now what we can do, we can just simply sum over all j. So, if we just sum it over all j from 1 to n, we can see that so we can group the elements. So, for example, when I equal to 0, so when I equal to 0, so you get exactly minus 1 power k e k, and then this term is going to be 1. So, and we are summing over from j to 1 to n. So, we get exactly n. Sorry, I am mixing n and k, and n is supposed to be k. So, this is supposed to be n. So, you have here n, and here n, and here also n. So, if you just sum it to over j, you can easily see that what we have is exactly minus 1 power n e n x 1 etc. x n, and then you have 1 plus 1 plus 1 n times, and similarly you have summation minus 1 power n minus I range from 1 to n e n minus I x 1 etc. x n, and then you will be just summing over x j I, j range from 1 to n. And note that this is just the power sum p I. So, this indeed gives minus 1 power n e n into that plus summation minus 1 power n minus I e n minus I p I equal to 0, where I range from 1 to n. And if you rewrite this, you get the Newton identity. You can call this also Newton identity, not a problem. So, this actually tells you that like PIs can be written in terms of EIs and vice versa. So, EIs also can be written as in terms of PIs. So, that means either you record EIs or record PIs. So, both will be storing the same data. So, that is what actually fundamental in developing the character theory. Okay, so I will stop here. So, we will continue with the character theory in the next class. Thank you.